We're continuing with part 2 of our solutions for assignment 2.14, reviewing limits. Question 39 is asking us about continuity at -1. Well, we can see that there's a domain issue for function f. We know that the radicand has to be at least 0. So if we move the negative x here, we know that our domain would say that x has to be less than or equal to -1. So it is, our domain would go from, I need an open endpoint, from -infinity to -1. So -1 is okay, gives us the square root of 0. So what does our graph look like here? At -1, we have a closed endpoint, and our graph goes this way. So is it continuous at -1? So our interesting question here is that at a closed endpoint, we say that the limit does exist, and because the endpoint is filled in. So remember, at a closed endpoint, that's our special case, we only require a one-sided limit. We only require a one-sided limit. So yes, it is continuous at -1. So I guess I should say our answer is yes. All right, in question 40, is it continuous at +4 rather? So our definition of continuity here, we're defined on both sides of 4, so we want to check, is our limit as we approach, I kind of keep changing here, as we approach 4 from the negative side, is that equal to our limit as we approach 4 from the positive side? And is that equivalent to what we get by direct substitution at 4? So is the hole in the graph plugged in other words? So let's find out. As x goes to 4 from the left side, we want to plug 4 into x squared minus 1. So that would be a 15. And 4 from the right side, we're using this part of the domain, so that would be a 15. And, I'm going to pause in a second and solve that problem so it doesn't keep happening. And f of 4, if I plug 4 in, I have a pop point. So here's the problem. Our limit is equal to 15. So the problem here is that the limit as x approaches 4 exists, but it is not equal to f of 4. So our overall limit was 15, but it does not get filled in. We have a pop point. So no, it is not continuous. No, it is not continuous, and this is our reason right here. All right. All right, given this information about limits, let's see if we can pick out the correct graph. As we approach -2 from the left and +2 from the left, our graph should be going to -infinity. So -2, we're going to -infinity. And at +2 on the left side, we're going to -infinity. As we approach -2 and +2 from the right side, we should be rising. So now this doesn't work. Oh, nope, -2 and +2 from the right side, we should be rising, and I guess it does work. And we should have a horizontal asymptote on the left end and the right end of 0. So the left end and the right end should be going to 0. So letter B seems to do the trick. All right, in 42, we just need to find the limits. So as we approach -2 from the small side, this would be our domain. So if we put -2 in for x, we'll get the square root of 0 is 0. If we approach -2 from the right side, that would give us this part of the domain. So we would approach -2 And does the overall limit exist? The left hand and the right hand limit did not agree, so there's no overall limit. All right, let's try the next one. As we approach positive 2 from the small side, positive 2 from the small side falls into this domain, so plugging 2 in. And as we approach 2 from the large side, we'll use this part of the domain. So let's plug in 2, and we'll get 4 minus 8 plus 6. 4 minus 8 is negative 4. Plus 6 is positive 2. The left and the right hand limits agree, so the overall limit exists there. Question 43, we want to find a constant that guarantees that the function will be continuous everywhere. Well, the only place we know this is a polynomial, sorry, didn't mean to jump there. This polynomial and this polynomial, we know that polynomials are continuous everywhere. So the only question in a piecewise defined function is, does one function pick up where the other one left off? So we know polynomial functions are continuous over the real numbers. So we need only check for continuity. At x equals 2. So we need the overall limit as x approaches 2. So as x approaches 2 from the small side, we need that to be equal to the limit as x approaches 2. Goodness, sorry, I'm not sure how I continue to switch that. Let's just write over the top of that. As x approaches 2 from the right side, goodness, ignore this while I try to close Windows. Oh dear, not a good time for updates to be coming. All right, let's try this again. The limit as we approach 2 from the right side, and we need to make sure that that's exactly what we get by direct substitution, putting 2 into our function. So as x approaches 2 from the small side, we'll have the first part of our domain. So this part will be c squared minus x squared. Now remember what x is going to be here. We're talking about when x goes to 2. So I can replace the x with 2. And the limit as x approaches 2 from the right side, we're going to use the other part of our function. And remember that x is approaching 2. So I can replace the x with a 2. And now these two things in this problem are exactly equal. So I need not write it twice. Okay, so let's see what we can solve here. C squared minus 4 is equal to 2c minus 4. Quadratic equation, so let's set it to 0. Add 4 to both sides. And please make sure that when you solve quadratics, you're expecting 2 different answers. And we could check to see whether either one of those should be thrown out. And I don't think that they have to, so I think both answers would be acceptable. So if c were equal to 0, we would have just negative x squared for the first domain. And if c were 0, we would have negative 2x for the second domain. And you could check it out. Is the opposite of x squared equal to 2 times x as x approaches 2? And that should work out okay. And equal to negative 2x. And when c is 2, we would have 4 minus x squared and 2 times the quantity 2 minus x. So both of them work. So we would come up with 2 answers for c that would both guarantee continuity. All right, for 44, The definition of continuity requires three things, and then we want to give an example with an equation and a graph to show how it might fail. So our first question for continuity is that f of x is defined at x equals a or x equals c, whatever constant you want. So for example, I think a typical one that we've used is the square root of x. The square root of x, sorry, I want to go to the positive side. The square root of x, f, is discontinuous at a equals, let's say, -5. Any negative for that value because it's not defined there. All right, our second question is, does the limit exist? The limit as x goes to a of f of x must exist. So where might that not happen? Well, we had lots of different choices. I'm having real trouble today with keeping my pen selected here, sorry. Any place that has a jump discontinuity, so you could write a piecewise defined function. You could write our absolute value over itself function. So we know this graph, the limit, goodness, that's becoming irritating here. Let's see if I can get back. Let me pause 1 second here. All right, let's see if I can continue any better here. I'm kind of overwhelming the window. All right, so we have this jump discontinuity. So our function is discontinuous. F is discontinuous at x equals 0 because the limit does not exist. And our third question, if I jump back up here, is when the limit exists, that might still have a pop point. So is it exactly equal to what we get when we directly substitute a into our function? So here our counterexample, something with a pop point. So let's do a simple case here. We know, for example, this rational function has a discontinuity at x equals 1. So let's give it a pop point. So you could make up any example you want. Notice when we cancel x minus 1 here, that we'll get x plus 1. And it has a discontinuity at 1. So we had this graph, and this discontinuity is at 2. And when x is equal to 1, we're way up here at 5. So is there a limit as we approach 1? Yes, the limit exists, but is the limit equal to f of 5? No. So here, because the limit as x approaches a of f of x is equal to 2, but that is not equal to 5, which is f of 1. So there's our counterexample for part 3. All right, 45, we're getting there. How can we clean this up? If we let h go to 0, do you see if h becomes 0, we'd have x to the 4th minus x to the 4th over 8 over 0. So 0 over 0 if we did direct substitution. So this question is actually leading us into our next unit. You might wonder why we're doing this. So let's actually see if we can factor and cancel. Well, how can we factor and cancel from such a thing? We need to know how to raise this to the 4th power. So our Pascal's triangle gives us our coefficients when we raise something. Oops, that's to the third power. Guess I need to go one more line here. There are our coefficients when we raise something to the fourth power. So we would have x to the fourth plus 4. X is down to the third power. H is up to the first power. Plus 6. X is down to the second power. H is up to the second. Our next coefficient is 4. X is down to the first. H is up to the third. And our last coefficient is 1. X is down to the 0 power. H is up to the fourth. And then we still, don't forget, we still have to keep this negative x to the fourth. So after we raise that to the fourth power, notice we've got a positive x to the fourth and a negative x to the fourth. So they are gone. And now look at all of our remaining terms. We can factor an h out of them. So now we would have 4x cubed plus 6x squared h to the first power plus 4x h to the second power plus h to the third. And I'm doing all of this. Whoops, and don't make this mistake. I'll count that against you, so I better not do it. The limit operator still has to appear on every line. But now we've solved our 0 over 0 problem because we can cancel by h. So we no longer have a 0 in the denominator, and now we can do direct substitution. Everywhere where we see an h, those terms are going to go to zeros. So what is left if all of these three terms become zeros? 4x cubed. 4 Come on, cooperate with me here, please. 4x cubed is the answer to our limit. So that might be the first time we've done one of those, but you'll see it again in the next few weeks. All right, question 46. Vertical motion problem. So first we're looking for average velocity over this time interval. So let's find the height at time 1 second. So we would have a negative 16 plus 64 plus 80, and our height at 3 seconds. And I think very quickly here, I see I'm going to pause, and I'm going to put this function into y1 of my calculator so that I can come up with these values. So once I pause, I'm going to find h of 0. That one I think I can tell is 80. And I'm going to find y1 of 2, and I'm going to do all of these while I've paused. And I'm really doing too many things on one page here of I'm using OneNote software, so I'm going to have to pause and clear here to get some memory back so that this isn't jumping around so much. I'm going to calculate these points and be right back with you. Okay, so I put this function into y1 editor, and of course then I change my variable to x. And then I went to the home screen and I found out what is y1 of 1, what is y1 of 3. So to do all of these on the home screen of your calculator. And we know this is an upside down parabola. So average velocities, how much distance have we covered? We know this is the fallacy of an average velocity here because our heights are equal. So the distance covered appears to be 0 in an elapsed time of 2. So we know here our distance, 128 minus 128 over our 2 seconds. So we come up with an average velocity of 0 feet per second. Well, we know why that's happening. If these heights are equal, that must mean that the vertex of our parabola happened to be right in between. So I think you should already be figuring out what you're expecting here is that the only way it reached the same height at those times was if it was symmetrical around the vertex. And you guys can go back to what you know from algebra. You know that your vertex has an x-coordinate of the opposite of b over 2a. So you maybe were one step ahead of me here. So you can see that when we put negative or 2 times negative 16. Do you see how you would agree that the vertex happens at 2 seconds? And we can see that again in part 3. At 0 seconds and at 4 seconds, the height is both 80. So at 0 seconds and 4 seconds, we're at these two positions on the quick sketch that I've made. So again, our average velocity, and let's write that this way, velocity average will be 0 feet per second. So we know that in those 4 seconds, it actually has traveled quite a distance. But because it ends right back where it started at, remember the object is traveling straight up and straight down. This is our graph over time. So the object itself is traveling straight up and straight down. So part 2 is the only one where we get an interesting answer. So our elapsed height and our elapsed time, goodness, 2 minus 0. So we would come up with 32 feet per second for our average velocity for part 2. So we can see some of the problems here. So what is the physical significance of an average velocity of 0? When will it occur? So when the two heights symmetrically surround the vertex. So it appears that our average velocity is 0, even though the object itself was covering quite a bit of ground. So the instantaneous velocity is much more important in a problem like this. So how can we approximate an instantaneous velocity when the projectile is only at one position? And we can't. The answer is that we can't do that. We need a displacement of time and distance, but we can cheat here using our calculator, and we can say, well, let's pick 2 times that are very, very close to 1 second. So remember that this is still an average velocity, but it is so close. So we're using the concept of a limit here, even before we've been able to prove it. So an elapsed distance divided by an elapsed time. So choose 2 values that are very close to 1 second. And then let's plug this in your calculator. And remember to put your numerator in parentheses. And your denominator, you probably would do that subtraction yourself. So let's find out on our calculators what we come up with to at least 3 decimal places. So when I calculated, I had 31.99999 with an 8 somewhere. So to 3 decimal places, I would get 32.000 feet per second. So you want to just make sure that you choose 2 values very close to 1 second. And now we're going to use a similar idea. I'm going to use the table feature of my calculator. So I'm going to put this function in as into my Y editor, and I'm going to choose X values that are very close to 0. So I told you that I liked having some symmetry to my graph, so I would like to get very, very close to 0 on either side. So let's see, I just counted 6 zeros. So 1, 2, 3, 4, 5, 6. And then I might do the same thing with only 4 zeros. And then I might try, and you might need to do more than this. We'll try just with 2 zeros. Remember that we need to do enough of these until we get accurate to 3 decimal places. So we're going to put this into our Y editor. Doesn't matter if you put it in as Y1 or whatever. Then we're going to go do an ask table. And you're going to put in these values. So I'm going to pause the video so you don't have to watch all of that, and then we'll see if we come up to some agreement. All right, so transferring these values, and I definitely got close enough, and in fact my calculator rounded these two values to 0. They're not exactly 0. To the calculator, though, you can see how close we were getting to 0 that the calculator couldn't contain enough digits. So they're getting closer and closer to 0. So I think we have a convincing table here to suspect that the limit of cosine x minus 1 over x as x goes to 0 is 0. Even though it's undefined at 0, there's a hole in the graph, but we suspect the hole in the graph will be at 0, 0. And this is going to also become a theorem that we're going to memorize in future assignments.